Good morning. Today we are going to see the steps that is in beams. So now we have classification based on support conditions in beams. We have simply supported beams, cantilever beams, and continuous beams. Now beam we will have very clear is a flexural member. Beam is flexural member, and therefore it is designed for shear force and bending moment. Designed for shear force and bending moment. As column, we are generally designing for axial force. So it is axial member. So steps to be followed. First, effective span, same as your slabs. Second, trial depth. Third, load calculations. Fourth, design moments. Fifth, check depth for bending moment. Sixth, main steel reinforcement. Seventh, check for deflection. Eighth, check for shear. And ninth, check for development length. You are not going to write in this mesh. You have to write in detail in all, in slabs also, in beams also, in columns also, in footing also. So steps you have to write down over there. So what is first step? Effective span. So you have to write effective span, which is given in clause number 22.2, page 34. Same for slab and beam. So you can see this one. So in exam, you have to use IS code. That is no problem. So what is expected? So simply supported slab, your effective span. This is most. You can write only this part. Clear span plus effective depth of slab or beam. So in this, you need not require slab or beam. You have to write down clear span plus effective depth of beam. Or we have center to center of support, whichever is less. So as we do not know depth of beam, so we will start with center to center distance of support. Then continuous beam. So these are the clauses. So in there you can write directly clear span plus effective depth. If question will ask, then you can go to this B part of the clause number, just that was on page number 34. So center to center distance, whichever is less. So if support is wider than 1 by 12 and smaller than 1 by 12, so we have to go in this fashion. Cantilever we have, that is from up to the face of the support plus half the effective depth. So this is your first step, center to center distance or clear span plus effective depth. Now trial depth. So in slabs we have trial depth, we are using, that is basic L by D ratio, and then by basic L by D ratio we are going for trial depth. But in beam we are going to find value of D, that is effective span upon (12 to 16). Now if load is less and span is smaller, we will go 16. If span is larger and load is more, then we will go 12. So likewise, you have to consider D equal to effective span upon 12 to 16. And then capital D, we are going to get D plus D dash. Now D dash, we are generally assuming over here, that is 40 millimeters. So we have this D dash 40 millimeter, and then from this we are going to get value of capital D. Now you can check it, your value of L effect, which will be clear span plus effective depth. But what happens in this case? In this case, your value of effective depth is always greater than your center to center distance. Sorry, that is center to center when we are going to find out. So we are going to add this width of support from both sides. And in this case, so BS by 2 from this, and bs by 2 from this. So this value generally we have 230 mm, and this effective depth is always greater than 230 mm, and therefore in most of the cases this criteria is not satisfied. Sorry, this criteria is not satisfied, and lesser value we have this only. So we can have in most of the beam problem center to center distance, that will be your distance is L effective in most of the cases. Most of the cases. And why that already mentioned? Because width of support, this is always less than effective depth in beam. Then we have next, that is load calculations. So actually width of slab we have to take 1 meter, and then we have to take load from slab. Now we have load from slab, first dead load, self weight plus floor finish, that is 25D. Already I mentioned 25 unit weight of concrete, unit is kilonewton per meter cube. D is depth of slab in meters. Then we have live load. So we have these two loads. So transfer of the load from slab to beam, in case of these are one-way slab. So in one-way slab, we do not have any load from slab to beam. Means on this beam, we do not have any load of slab. But on this longer beam, we have half the portion. So that is Lx1 by 2. This portion load will be on this beam. So on middle beam, we have that is from both. This load also comes over there. This load also comes over there. So that load we have to consider on beams. That is load from slab. Then we have, if we have two-way slab, now here we have two-way slab. In case of two-way slab, so you have to write over there when you are writing this step. In case of two-way slab, so on longer beam, we have trapezoidal load. On shorter beam, we have that is triangular load. So these loads we should know. Then how we will find equivalent load, that you should know. W equivalent. For flexure, we have W Lx by 3. Then that is triangle. Now check formulas. Then W equivalent, we have W Lx by 2 in bracket 1 minus 1 upon 3 beta square. Similarly, check for your shear force also. This is W equivalent for trapezoidal. Now, once you know these values, that is dead load from slab, so you can have this, that is given in figure 7. If examiner asks where you have these values, then that are clause number 24.5. Then total load we have, total dead load. We have load from slab, then self weight of beam, and third weight from wall. Self weight of beam, we are going to consider 25 B into D. That will be self weight. We will get in kilonewton per meter. This value we are getting it as kilonewton per meter. Now weight from wall. So we are going to consider gamma masonry. And then we have to multiply it by width of that wall, multiply by height of that wall. So gamma masonry value generally taken as 18 to 20 kilonewton per meter cube. And then multiplied B in meters, height in meters, and then you are going to get this total dead load from there. So total dead load. Do not make it ultimate, keep as it is. Then you have total live load. So this is B part. So in B part, we have total live load. So I will mention this as WD only. And then this live load I will mention is as WL. Then we have, these will be the loads on the beam. Now, when you have simply supported slabs, then you can add this and you can go 1.5 WD plus WL. And then we will have, this will be directly factored load. In case of simply supported and in case of cantilever, in both. In both, we have to go directly add dead load to live load. So WT you can say equal to WD plus WL, and then you can multiply this WT. So you can write this value is WUT, which you will get from here. And then you can have this bending moment. So design moments. So sorry, this is not a slab. So we have this as beam. So now simply supported beam. So WUT you can write WUT L square by 8, and WUT we have seen we have 1.5 WD plus WL. Then we have cantilever beam. So I have taken slide of slab. So for cantilever beam we have WUT again L square by 2. Then we have for continuous slab, we have to go to clause number 22.4.1, arrangement of imposed loads. And actually, if we will see design dead load on all spans with full design imposed load on adjacent two spans and design load. And second, when design imposed load does not exceed 3/4 of the design load, the load arrangements may be taken as in this fashion. Now here, so we are not interested with this. Now design load on all spans with full design imposed load on two adjacent spans. So dead load is always on all spans and with imposed load on two adjacent spans. This condition is for maximum bending moment at support. Maximum bending moment at support. Keep in mind, the examiner may ask you what are these conditions. And then on alternate slab, so this is for maximum bending moment for span moment. For span moment. So now for beams and slab continuous over support 22.4. So for continuous support, you have to use 22.4.1. So this we are not going to use. Then we have this that is given on page number 34. You can go 22.4.1. So now if I will go for the plotting of this loading diagram. So now for both the case, you have to draw the dead load. So dead load is always there. So dead load position we are going to consider on all span in all the cases. So this is my dead load. Now if I have to go for support, so if I will mention this A, B, C, D. Now they have mentioned when I will go for maximum bending moment, that is for support, then in that case, I have to apply live load on adjacent span of the support. So the spans which are connected to the support, on this we have to apply live load. So this is live load. And then we have this also live load. So on these spans, we have 1.5 dead load plus live load. Means we have this as WUT. Whereas here we have only WD. That is due to dead load, not factored, not WUD. Why? Because when you will consider WD, then your distribution will be less. Now, do not go in detail. Distribution is less, and you will get maximum moment at support B. And therefore, we are going this condition for maximum support at B. Now, if we will go maximum support at C, then you have to apply 1.5 total load on BC and CD, because at support C and for support C, connected spans are CB and CD. For B, connected spans are BA and BC. So whatever connected span are to this support, you have to apply total load. And on alternate span, you have dead load, dead load, total load. So then we have second condition, that is for maximum span moment. So they have mentioned over there for maximum span moment, we have on that span total load. Adjacent we have only dead load. So if I will mention over here, we are in this page. So we have now suppose this is A, B, C, D. Now if I have to go for maximum span moment BC, maximum span moment BC, then I have to apply you. So on this we have only WD, dead load. Here also we have WD. And on this span where we are interested with maximum value, then we have 1.5, sorry, till this only. Just 1 minute. So we have till this only. BC, we have WUT. So WUT, that is 1.5 dead load plus a live load. So that is WD and WN. So if you have a span on this side, then you have total again, WUT. So alternately, we have to go for this. So this will be WUT. If you are on this side, WUT. In this, if you are on this side, then you have only dead load, WD. So on this side, WD. If you are on this side again, then we have WUT. Alternate, we have WUT. So the spans adjacent to the support, we have WUT. Adjacent to these spans, we have WD. Again, adjacent to it, WUT in the same fashion. If I have to go for AB, then we have to apply loading condition for AB, maximum span moment AB. Then we have WUT on AB, then WD on BC, and WUT on CD. So likewise, you have to provide these arrangements, and then you have to find fixed end moments. Sorry, you have to find final moments. Final moments, and that we have to use to find the reinforcement. So second, we can have this will be 1 by 12. So table 12 and table 13, already you are familiar with this. So they may ask you to draw the diagram of these coefficients. You should be in position. Calculations will not be there. So we can have likewise. So values you have to plot coefficient 0. First I am plotting of supports. Next to end support, we have 1 by 10. And then at other interior support, that is minus 1 by 10, we have this will be minus 1 by 12. This is again next to end support 1 by 10. And then for this is for dead load and for imposed load. So these are for dead load. Here we have 0. For imposed load, the values are given as minus 1 by 9. Everywhere we have that is minus 1 by 9 and minus 1 by 9, 0. So here also we have 0. This is due to imposed load. Imposed load. Then these are for support moment. If I will go for span moment, then for span moment, so we have this value minus 1 by 10. minus 1 by 9. Now, if I will go for span moment, then I have to draw these values in this fashion. So we have dead load. So you can see we have near to near middle of end support 1 by 12, at middle of interior 1 by 16, means we have this value 1 by 12, we have 1 by 16, 1 by 16 and 1 by 12. And then these are for dead load. For imposed load, they have given these values, that is 1 by 10, then 1 by 12, 1 by 12 and 1 by 10. So now you can see critical values, means maximum moment we will always get next to the end support, because this is in denominator and denominator value is less, the numerator we will get more, because we are going to multiply for all these by WUL square. So if WL square by 10, this is lesser one compared with this all 12, 16. So here also we have 1 by 12. 1 by 9 is there, but 1 by 12. So this value is lesser. So this 1 by 10, that is maximum value in all these cases. So maximum moment we have always next to the end support. So then we have actually a redistribution of moments. So once we got these values, and if we asked what is the redistribution, so why we will go redistribution, that is most important one. So we have, if I will go for the bending moment diagram, then we have bending moment diagram in this fashion. Now at support we will have beam as a rectangular beam. So at support we have rectangular beam. And in span we have T or L beam. Span moment we have, listen carefully, T or L beam. So our capacity is very large in this region where we have T beam, and load coming on it is lesser compared with support. So what we are going here, as at support we have rectangular beam, we are going to reduce the moment at support, and transfer it to the span moment. Span moment already we have capacity, so section required is not more in span moment, as it is T beam and your capacity of T beam is much larger, that is around 5 to 6 times that of rectangular. 5 to 6 times that of rectangular, and therefore we are going to redistribute it. Now you have to go through the curve that we have drawn in the class. We have 3 curves. First curve we have, that is actual bending moment diagram. Then we are going to reduce this bending moment diagram by the value that is of support. Suppose we have support 100, and if we have redistribution is given 20%, then we are going to reduce all the values, or we are going to draw a parallel curve reducing all values by 20. Reducing all values by 20. So this curve is parallel to this. And we are going to plot third curve by reducing value of that point by 20%. So as it is 0, so it will become 0. This value is reduced over here, 0, and then we have this will be. Here values are reduced of each point by 20%, and in this curve we are taking curve by 20 kilonewton per meter downwards. So this is 80, and this value we have taken distribution, that is 20%, so this is 20. So 3 curves. First curve actual BM, second curve reduce this BM by actual BM by percentage of redistribution, and third reduce each value by 20%. Reduce each value by 20%. You should be in position to answer this redistribution of moment. Then check depth for bending moment. Maximum moment already I mentioned. Next to end support. Support next to end support. And from there you have to find, there we have as next to support, next to end support. And this support is rectangular. And therefore you have to take B as 230 mm or 250 mm or 300 as per given. Then RU max, you should be in position. So while calculating values of slab load, you have to take value that is B as 1 meter in slab, not in beam. So otherwise you will take it in beam. So this is for slab, and for beam we have this value 230, 250 or 300 mm. That you have to keep in mind. So in beams we should be careful. Value should be in this fashion. RU max already we know, we have this formula that may be asked. Reinforcement, we have this formula, minimum reinforcement. Actually this mild steel reinforcement in either direction in slab. So some examiner may say this is for your slab, what is for your beams. So that also I have mentioned, given in page, on page number 46. So if you will ask minimum reinforcement for beams, then you can say this 26.5.1, that is minimum reinforcement. So do not say that is of slab. He may take objection on this. So better go for page number 46, minimum area of tension reinforcement. And we have this value. This value actually we have used. If you remember, we have used this formula in footing. So you can go to that footing and you can see how we have used this formula for footing to calculate reinforcement. So you can go for this. So reinforcement for beams generally answer for 26.5.1, and slab we can have, just I have shown you for slab clause number 26.5.2.1, and this is 26.5.1. Then check for deflection, you know this one, I will not go in detail with this. Check for deflection, all these criteria. Check for shear also, we are same fashion. So already you have gone through it. Then we have shear, and that already I mentioned. You have, if you will go for shear reinforcement, and if we have diagram in this fashion, then we have in this region spacing is less. Spacing less, and in middle 1/3 we have spacing more, because shear force is less, spacing more. And critical, that we know, that is a distance d from face of the support for your shear force. Then development length, that we have taken in detail in one problem, that you have to see it, how we will consider these values of tau bd for tension, for compression, that are mentioned over here. So we have to increase for torr steel deform bars by 60%, and then if compression 25%. So if we have tension, this tau b becomes 1.6 into tau bd, and if we have compression, that is bars in compression, then we have this value. For compression, we have this value. This is for deform bars. Means we have for Fe 415 and 500. And for compression, we have to again multiply it by 1.25. So likewise, you have to go for development length, and then you have to find it. So these values actually I explain. If we will go to slabs, that is given in detail. So I will not go in detail. I already shared this video to you, how we are going to consider this. If we have vertical bend, means 90-degree bend, and second we have that is hook. So you just listen it carefully. Video of slab, in that one it is very given very clearly. So this is explained here. In slab, same I have used over here. So go in slab in detail for development length. So now we will stop here only. So thank you.